deeply sorry. The delay is completely my fault. Right, so today we now start with a panel discussion, which is about features and principles of quantum gravity, in particular degrees of freedom, non-locality, and non-commutativity. As before, these are very vague titles, and I think everybody can sort of fill it in their own way. My job here is mainly as a chair, because I'm completely ignorant of these three words. And also, I want to mention that maybe this is good, because display of ignorance is also needed if we want to get interaction with here are all the experts with the non-experts, okay? So I will show me being naive, and so I will just do something because they asked me to do it. So I just have a few questions, but I think they're way less important than what the panel members will say. So of course, what this is about, I guess, is what are the fundamental features and degrees of freedom of quantum gravity? Is it a theory of the metric, or is it something else? And related to that, I think for me, it fits with the question, how general is holography? Because holography has told us that maybe we should think about quantum gravity completely different. Obviously, the question then is space and non-commutativity, because it was part of the title, and we didn't hear much about it yet in the conference. Should space-time, this is, I think, maybe essential part, and the different talks we heard, the different approaches, should space-time be emergent, or is it something that we'll put in by hand? In a similar spirit, should we quantize relativity, if we want to do more than effective field theory? Or should relativity come out? I guess these are like the general question. Maybe more specific is the following. So gravity is perturbatively at least non-renormalizable. Do we here all agree that therefore its UV completion requires new degrees of freedom? And imagine we agree. Is it a finite number or is it an infinite number of extra degrees of freedom? We already heard how non-locality seems to be crucial. It's considered to be maybe the feature to understand black hole information. So a question that I have personally is can we quantify how much non-locality there is? Is there like a notion of a scale at which non-locality kicks in? And if so, does it lead to a reduction of degrees of freedom, as we, for instance, see in holography? Because holography, I think, is an extreme notion of non-locality. And then a general question I had when I hear about the different approaches to quantum gravity, I sometimes wonder, could it be that we all agree, maybe on the same theories when we are in 2 or 3 dimensions? It's sometimes a feeling that you have when you listen to these talks, that the lower you go in dimension, maybe the more we all agree with each other. Right, but okay. So I would say, maybe in the order of the way people are sitting, or maybe since I'm on the laptop, we can do it with the people who send me the slides. So maybe, Stephen, if I open your slides, you could be the first. So you just can use the cursor.
Yeah. Thank you. Okay, so features of a theory of quantum gravity. Just a reminder, of course, our collective goal is a quantum theory of gravity, and my emphasis on that will become clear in a moment. But the traditional approach to that has, of course, been very well represented here. And the traditional approach is begin with the classical theory and quantize it. That has been traditionally done specifically with general relativity, with or without new variables, in some discretized form, etc. That also is the general approach that is taken to string theory as well. But that traditional approach has led to very vexing problems. Initially, the problem of non-renormalizability, which had been the big focus of sort of the trouble with quantum gravity over many decades, in fact. Non-renormalizability amounts to non-predictivity. But with a somewhat more modern viewpoint, we might be a little less bothered by this, both because it's only really a short distance problem, and there are ways of addressing the non-renormalizability problem. String theory, of course, addresses perturbative non-renormalizability. And some of these other approaches get at that question also. But what we've realized over time is that there is apparently a more profound problem, which is the problem of non-unitarity in gravity, or at least the apparent non-unitarity, which we understand to be basically a long distance problem. It's associated with, say, quantum black hole formation. And actually, let me see, I think my slide is being cut off.
Yeah, scroll down.
Yeah,
It's not full screen.
There we go. Okay. So how do
I do the full screen. I should know.
Yeah, maybe like bottom right. So there is a 1 to 1 and then
yes, if I can get the cursor to go there. Oh, the cursor.
Is that Control L?
Control L.
control.
Yeah.
Yeah. Wait.
Full screen.
Well, okay. Everyone in the back can see it. Let's just go with it and not waste time. Okay.
It was better before.
It was better before.
It was better, yeah, except you couldn't see the bottom line. Well, how do I get out of control?
It will start here on the lower half of the
Secondary avoid.
I think
Oh, okay, okay,
of the whole monster.
okay, so I'll just scroll.
Just we all have photographic memories.
Scroll.
Yeah, I dropped my laptop. It doesn't work.
There we go. Okay, there we go. Oh, no. Okay, I don't know why that. Oh, but
You click once more. Yeah.
there, okay. Okay, so again, non-unitarity, apparent non-unitarity associated with the problem of quantum black holes. And that appears to be a long distance problem and therefore really a more profound problem, apparently, it seems. So given the problems we have with traditional approaches, a proposed alternative is really to take a quantum first approach to turn things around and not try to quantize geometry, say, but to think about how to provide gravitational structure to a quantum theory, is one way of putting it. So the basic idea is begin with the structure of quantum mechanics and then describe additional structure appropriate for describing gravity, plus of course matter, fields, and so on. Some inspiration for this viewpoint comes from the algebraic approach to quantum field theory, which very much is stated in this spirit. You begin with a Hilbert space and endow that Hilbert space with some additional structure, a net of subalgebras. Of course, I don't have time to fully describe that here, but you can read, say, Hogg's book or something like that. And that net of subalgebras encodes the structure of the underlying manifold. And that's how you put in locality and so on and so forth, and much of the structure of quantum field theory. And so this way of thinking about things, I think, drives directly at this question of the expected features of quantum gravity. And so let's just think briefly about expected features in this context. So, of course, again, to emphasize, we want to start with the structure of quantum mechanics. So what is that? Well, we don't have all the familiar apparatus of standard quantum mechanics, for example, time and Hamiltonians necessarily in gravity, but sort of universal features are a linear space of states, something like a Hilbert space, quantum observables or Hermitian operators, say, on that space, and for at least appropriate states, appropriate sectors of the theory, unitarity of the S matrix. Say specifically for sectors that correspond to perturbations of the Minkowski vacuum, excitations created on top of the Minkowski vacuum, which we might assume is a sensible state, that and the perturbations about it. So that's a starting point, but clearly, we need more than this structure if we're going to describe gravity. And what clues do we have towards that structure? And here we talk a little bit about expectations. And so, well, one set of clues, again, reminding ourselves that the additional mathematical structure, if we think about quantum field theory, is the net of subalgebras. One set of clues is that whatever the structure is on this Hilbert space, there should be a correspondence limit. That structure should match on the local quantum field theory plus perturbative or semi-classical gravity in weak gravity situations appropriately defined. A second thing is at the fundamental mathematical level, we would like to understand this notion of localization of information. We need something like a definition of subsystems, perhaps only approximate for gravity, for gravitational systems, a notion of Einstein separability, so that we basically can do physics. You need a way of sort of discussing different degrees of freedom, which in field theory are associated with different regions. But the problem with the field theory way of describing things is that, well, naive microcausality fails in quantum gravity. We see that, you know, using this first principle, the notion of correspondence, because deleting perturbative order, we can just explicitly see the failure of microcausality, the failure of commutativity with observables outside the light cone. So a big question is, what is that other structure on the Hilbert space? It's not obviously tensor factorization, which is how you describe subsystems, say for locally finite systems, tensor factorization of the Hilbert space. It's not obviously this subalgebra structure appropriate to field theory. It's some modification of that. And that's, I think, an important clue, you know, that we should have a structure like this that gives us, you know, sort of in the weak gravity limit, reduces to the structure of nets of subalgebras. And then finally, another expected feature for quantum gravity is we should, you know, have some state selection principle, something like a, well, something that reduces the correspondence limit to essentially the Wheeler-DeWitt equation in some version. So those are some suggestions for what we're looking for, but I just want to stress, it really looks like the quantum field theory paradigm is likely not the right paradigm to start with to describe quantum gravity. We need something with an intrinsically apparently different structure because, you know, quantum field theory is sort of too local to, for example, give us unitarity in the context of black holes. And likewise, discrete geometry approaches seem too local. They don't have this long distance modification of the theory that we apparently need if we're going to describe unitary black hole formation and evaporation. That's one reason. And of course, just again, even at the naive perturbative level, microcausality you can show directly fails in terms of commutativity of observables that are danger. So those are just some thoughts.
Great, thank you. Since I have the slides of Daniele here, you see it's also small, but should be okay. More? I think it's okay.
Okay. So the many questions that you suggested to address, I realized that I had the answer to none of them, but I decided to focus on just one and express ignorance about only a single issue. So the first question, so the question is whether quantum gravity will be or is some form of quantized general relativity or the result of quantizing some other classical gravitational theory, or is it a quantum theory or some new type of degrees of freedom? And new means not fields based on this, on a manifold and space-time manifold and so on. And I have the answer to that, and the answer is that I have no idea. It's one of the other. I couldn't come up. I thought hard for an hour whether I could come up at least some argument in favor of one option or the other, either from physics or from mathematics or from religion or sports. I couldn't come up with any decisive direction. But my point, the only point I'm going to make is that it doesn't matter to a large extent, because in both cases, space-time and geometry are emergent the only thing that changes is the level or the degree to which they are emerging in one option or the other, and therefore in one approach or the other. Suppose that the metric and other spacetime fields are fundamental. That's your ontology. Sorry for the word for this word. If that's your ontology, then okay, you know what the degrees of freedom are, but you have to quantize that. Those fundamental entities have to be dealt with in some maybe generalized quantum mechanical framework. Fine. But for the little I know about quantum mechanics, that already implies that geometries are going to be superposed, that geometric observables are going to be subject to Heisenberg uncertainty, so they will not commute in general. That therefore you're going to have fluctuations of those observables, but if the geometries themselves are superposed and fluctuating, then the causal structure and the causal properties that we attribute to space-time physics, that we use in space-time physics, are going to be subject to fluctuations. And I'm not even touching on even more esoteric aspects of quantum mechanics, like contextuality. And again, this is a sort of, I'm not changing the degrees of freedom. I'm just saying, well, there is some version of quantum mechanics where we are incorporating most, or at least some of the features that make quantum mechanics so puzzling and interesting for those degrees of freedom. Well, that follows. It also means that there will be no single quantum state of geometry that will correspond to, that will encode a precise value for all geometric quantities. That's exactly what we should have learned, that cannot be the case in going from classical to quantum. And plus, quantum states of geometry with this partial information encoded in each of them are then going to be generic universal proposition. If you go a little bit more specific about the gravitational case, we've heard in previous days that local space-time observables are relational. The only meaningful way in a different variant sense of constructing local quantities is relational, meaning in relation between a system you're trying to localize and a physical frame that defines what you mean by space-time localization, a clock and 3 rods. So it's a definition of what you mean by space-time. It's not like something that goes in a certain way with respect to time, independently defined. But physical frames, again, bringing together the previous pieces, physical frames are themselves, if they're physical, gravitating, interacting, maybe self-interacting, and quantum. So themselves subject to superposition and all of that. The result is that space-time as we know it, so from the relativity, the usual fields, the precise determination of space-time quantities, causal structure, and all of that emerges only in some semi-classical approximation or whatever is the result of quantizing the classical gravitational theory. So it's still an emergent thing. It's emergence in a sort of weaker sense than it could possibly be, and I would move on to the next point, but it's still emergent. So we cannot rely on those space-time notions in formulating the theory. And this is the conservative, trivial case. You take a classical theory, you apply some quantization algorithm, you are super smart, you can do it to the end, it works, that's the theory. If the metric and other fields are effective collective entities that somehow you have to reconstruct out of more fundamental quantum degrees of freedom, whatever they are, and even if they are straightforward, mild generalization of smooth geometries and smooth fields, like piecewise flat geometries, some piecewise degenerate things, or mildly singular generalization of usual smooth fields, or some other form of discrete structure. Well, it just means that space-time is emerging in a stronger sense because there is a further set and levels of approximations you have to go through. And therefore, further ways in which, if you read in the other direction, the usual space-time notions break down or acquire modifications. So if there is to put it differently, if there is the necessity for some procedure to get to the very notion, some closed graining or collective dynamics that leads is required to get to the notion of a smooth field, maybe a quantum metric field. Well, this comes with additional distance from the usual understanding of space-time. It's a further level of distance. Therefore, especially if you give to the new entities that you have to force grain an ontological significance, so they're not just regularization tools, but somehow you tentatively say, well, these are the physical structures, the more fundamental structures, then you get new issues. It means that in the fundamental theory, there's simply no standard notion of space, time, and geometry. And this is not just because the usual notions are subject to quantum fluctuations or superpositions. They're not there. Moreover, when you take continuum limits or coarse graining, you should expect that the system will have different continuum phases. In one of them, there should be geometry because, well, it seems to work. So in one of them, there is space-time in some approximation, but there will be other regimes of the theory, other phases in which under the same approximation, under the same continuum limit, space-time and geometry just cannot be reconstructed, even after such coarse graining. It's a bit like you have atoms or molecules, you take continuum limits, of course, depending on the range of parameters you're fixing, you get to the liquid, gas, solid phase. And if in this picture, space-time and geometry are like an effective coarse-grained description, one such phase, the others are just as physical, but still not spatial-temporal, even in a continuum limit. It's something else. So a quantum space-time in the sense of the first possibility only emerged after some sort of continuum, for lack of a better word, some new type of approximation, and in some particular range of parameters. Now, therefore, what should I expect about the usual, what are the features of quantum gravity, or what couldn't be, or cannot be, or I should not expect to be fundamental features of quantum gravity? Should I expect space-time non-commutativity or non-locality? You should expect violation of unitarity. Should I expect indefinite causality? Personally, I expect all of it. And the real question is, at which one is recovered first so that I can rely on it in addressing the violations of the others. In the case of black holes, of which I'm not an expert, I'm fine with trying to, for me, it seems that insisting on having a unitary evolution at the cost of non-locality, for example, which is, I find it reasonable, is just the translation of expecting that the breakdown of unitarity comes later or after the breakdown of locality, and not that unitarity is somehow fundamental. It's just a sort of, which one breaks down first, or is more robust, or is recovered first, really the other way around. So I close with just two comments, two more. Exactly because the usual effective field theory intuition is based on all those ingredients, unitarity, causality, locality, and so on. Well, I expect it to be misleading. I have no idea at which point it's misleading. Where is it that I should stop using it? Or vice versa. To what extent I can push it? I'm very happy with people pushing it as much as possible. But it's probably misleading. In particular, even the notion of a Planck scale as the relevant scale at which this new principle will apply, or the usual principle breakdown, well, is derived within the context of using the couplings of the theories we know breakdown. And I'm not really sure that the relevant scale for quantum gravity is the Planck scale. In a separate but related note, I'm not sure that we should rely at all on any notion of a separation of scales, because even that relies on the existence of a background geometry, the effective field theory principles, and so on. As I said, as I was promising, I'm just expressing ignorance, not just no answer. One thing that has never been touched upon in the previous days, and I find it somehow surprising, is that I expect that quantum gravity will lead to some reassessment, will force us to reassess foundations of quantum mechanics, not because we don't have enough problems trying to construct the theory of quantum gravity, but because of what I said earlier. Even if we try to stick as much as possible to the usual formalism of quantum mechanics, for example, following what Steve was suggesting, you try to usual notion of Hilbert space, algebras of observables constructed maybe in a modified, novel manner. If you don't have unitarity as a fundamental thing for generic things, for the whole theory, you don't have the locality, and causality is also indefinite. I'm frankly not sure how much of any of the usual interpretations of quantum mechanics, from the most orthodox to the most exotic ones, can be applied. Can still be there. All of them are very much space-time based. So, well, we should think also that direction in parallel with our other problems. Then we are a big community, so each one decides which problem to focus on and which one are more congenial to your skills, expertise, and interests, but they're all relevant.
Thank you. Said when I would be a chair of your time, we are not on time. No, don't worry. I think the remaining three people have no slides. Is that correct? So yeah.
There are just two of us.
Alexey.
Alex, I'm sorry.
I have board.
Alexey. Go.
We have board, yeah? No, I will use a board.
Oh, you will use a board, okay. But I will freewheel.
Perfect. Please go ahead.
Okay, all right, good. Yeah, so it won't surprise people that I will take, I'm interested in UV, and it's of course an issue of to what extent this talks to IR issues that people want quantum gravity to solve. So I'm really interested in the non-perturbative sector. And I would say I also go there with the benefit, without wanting to boast, of having computational access, as I was describing in my talk, to that sector by these lattice methods. And that do put things in a very different perspectives, because you realize even for, kind of quite broad ideas that are floating around, you have to ask yourself, how realistic is it that I will be able to address this type of question with the tools that are the best mathematical computational tools that are available to me? And is that, is the problem computationally in some sense? If it isn't, I will never be able to derive any predictions from it. Or is it not? And already that seems a very, simple step. At that first step, many aspects in quantum gravity, that people float, end up in the wishful thinking forever category. In the sense that, if one really looks at it, it's very unobvious, unless someone comes up with some magic wand. You never know. And people like something that I don't really like. Let's wait for the next Einstein. Well, apart from the sexism that's implied, I'm not so sure the next, people who don't have an education in this field will be able, the surfer dudes will be able to address these problems. In a way, we are at a rather refined level of, abstract theory. Of course, we try to relate it to real physics.
What do you know about surfer dudes?
Very, very. Are you one of them?
No, I'm not.
I'm speaking in cliches, but I hope you understand my point. I don't want to insult any particular individual.
It was a joke.
Yeah. Right, so I'm already in hot water here. Okay, but I'm going, so we're going to the plan state. So I want to talk a little bit about degrees of freedom, because that was one of the topics, and it's a great apropos for many things. So I would say, if in a more narrow sense, I think that's also how you interpreted the question, you're saying, okay, we have to quantize gravity as part of a unified kind of gravity unified theory, where we have a dynamical principle that includes all matter, everything we know and maybe much more? Or is it okay to just talk about pure quantum gravity in a sense? So I would say, again, there's a community views, they shift throughout time. In the old days, it was perfectly fine to not, to just work on quantum gravity. But then along came superstring theory as, the unique way of quantizing gravity. Obviously, it had to be all there and was a unifying principle. Now, I think we are in a little bit of a backlash. So, and if then, well, there are also other people, I would say, who argue very much that matter must be there because otherwise there's no observer. And so what are we talking about? What I mean with pure quantum gravity, however, is, we're writing down theories for the metric or the connection or for some maybe slightly generalized set of things. Can we formulate meaningful theories that satisfy logical consistency, have observers, etc.? And we have such models. I mean, even if you look at 2D quantum gravity, there are models that are perfectly interesting and have interesting structures in them without any matter coupling. Of course, it doesn't preclude matter coupling. So I think also that, you can only possibly make sense if you are grand unified. I think that's a little bit on the way out as a philosophical point. And I think, or as a prejudice. But of course, some people still hold strongly onto this view. And well, it's fine. I think there is no way currently decide whether it's one or the other. Does it have to be unified? And what do we mean by that? Okay, so now allow myself to just talk about pure quantum gravity. And then people can say, okay, there's still issues. Is it just, what is it? Metric, geometry, generalized metric, some discretized form of things. Oh, let me add torsion. Oh, let me add topology. So there is still seemingly, a large choice of possibilities that are at least there out in, theory space, thought space, what we might be able to do. Okay? So let me zoom in on one particular thing, and that's, counting of degrees of freedom. What can we say about that? Okay, if someone hands me a classical field theory, and I should figure out what the degrees of freedom are, then I think, oh gosh, now I have to do another Dirac analysis, right? So I have to work out what are the physical degrees of freedom. I have to apply, I have to find what the constraints are, what is physical, what's not physical. But there is in principle, a well-defined way to understand what the physical degrees of freedom are. Yeah, if you're talking about the relativistic quantum theory, I just have to check what the particle content is of my theory, right? That's kind of fairly easy, and then I just count those. Now, if I go to a very non-perturbative regime, it seems to me it's not a priori clear what we mean by counting the degrees of freedom. Yeah? So if it happens that, you can find some effective theory that, let's say, that's a conformal field theory at very, very, very high energies, you might be able to apply some traditional kind of degree of freedom counting. You recognize what kind of conformal field theory that is, and you may be able to say something about the degrees of freedom. But to talk with Daniele, why should things be nice in the UV? So if it's something messy and I don't know, some quantum fluctuating metric degrees of freedom, well, I'm not even sure that question makes sense. So one should be very careful, people like myself, they're hammering on, well, what are the observables? I think it's a very good question, because if you're striving also in our mapping, the gravity, there's a quantum to the classical stuff. If you want to really apply that for every element of our theory construction, I think we will never get anywhere, because there's so much in there that's just also formalism and also degrees of freedom. So I think we're making our life very difficult. Okay, so here now, nevertheless, you seem to be still faced with a huge number of choices to make when you want to do quantum gravity, even if you're talking about the degrees of freedom. Yeah, so the inclusion of topology is one thing. So again, if you have now a concrete computational framework, and part of the discussion this morning related to this, then the thing is, am I just writing down, partition functions or path integrals that have this formal integration over, well, a class of those metrics, a class of those other things, and then people here, Daniele advertised, well, the Feynman principle is sum over everything that's there. Well, that it just doesn't work. It doesn't make mathematical sense, and you cannot make mathematical sense of it because it's a too large, set of objects potentially, and it's get to huge infinities which we have no idea how to renormalize, and get physics and therefore predictions out of it. So a point I want to make is there are, although our imagination, say, of what we want to have included in the path integral is virtually unlimited. If you really want to say, no, I want to extract predictions, and therefore I have to be able, some approximations, renormalization, reasonably well controlled ways in which you get rid of infinities which are there. If you cannot do that, then you will have a very hard time in deriving any predictions. If you take that point of view, so what's feasible for me to integrate over or to sum over, you will realize that there's actually, only a small window of opportunity. So I don't know what it looks like in anyone's particular approach, but if I look at kind of lattice type things, and also stuff that like Daniele was talking about, where one talks about piecewise fed geometries. Okay, so these are very nice objects, but they can become very nasty. For instance, if they are non-manifold-like. That's one thing that came up. If one includes topologies, well, we get very, 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 very many of them. So there is on the one hand, if in a chosen regularization, you are too sparse in the way you kind of probe your configuration space, you don't get anything interesting out because then your gravitational degrees of freedom are not even there. If on the other hand you choose too many things, well, either you get infinities you simply cannot control, or you get just overwhelmed by things that never lead to a sensible gravity, space-times, the emergent space-times that people like to talk about. So, for example, if you allow yourself to include topologies, well, number one, beyond 2 dimensions, we have no idea how to do this sum. Yeah? But you see, in this kind of lattice approaches, what happens is that there are many, many more local topological degrees of freedom than there are geometric degrees of freedom. So whatever you're doing, and you're taking some continuum limit, if you insist on that sum over topologies, unless you're, again, there's some magic wand you find somewhere, then the topological degrees of freedom will totally overwhelm the local geometric degrees of freedom. Will you ever be able to show that a 4-dimensional space-time emerges from such a structure? I challenge you to show this, but it's very, very, very non-trivial. And that now relates to the emergence of space-time that was also part of the question. So emergent is very fashionable. Everything emerges all the time. But if you're talking about emergence in a more statistical mechanical sense, where I have a system with certain microscopic degrees of freedom, and I'm putting in some these building blocks have some properties. I let them interact to certain rules, and then I look at the collective behavior of those, and then I zoom out. Do I find, in this case, something that reminds me of a 4-dimensional space-time, or do I just see gibberish? So people have studied these statistical models, which work with these geometrical building blocks in dimensions, 2, 3, 4, even higher. And it turns out, unless I do something very special, what I get is just nonsense. So nothing that reminds me in any way of a 4D, on any scale of a 4D space-time. So just to say, it seems, to some extent that quantum gravity is maybe a free line at the Planck scale, but in reality, it is not so.
Thank you, Renate. Would you be next?
I find your questions very useful, so I'm going to try and stick to them as much as possible. So, because the answers to them depend on your the approach that you're answering them within. So some questions I find it easy to answer within causal set theory, which is the theory I know most about. So let me answer as many as I can within that, the context of that. So what are the fundamental degrees of freedom of quantum gravity? In causal set theory, they are discrete order relations. That's what they are. And is space-time emergent? The answer is yes, because there's no space-time a causal set by itself is not a space-time. Generically, it's not a space-time. Okay, so I think I couldn't really answer any of those specifically within causal set theory, but let me address the question: how general is holography, which is a super interesting question. So for me, holography, not an expert, but it has these two features, one of which, I mean, they both crop up when you read papers, one of which is the state or the idea that, proposal that there are finitely many degrees of freedom in a finite space-time volume, roughly, right? So, or the dimension of the Hilbert space that describes the degrees of freedom in a finite region of space-time is finite. So I think that is quite that's quite I mean, I think that's quite a general perspective. I think a lot of approaches to the problem, and it's certainly true in causal set theory, but I think it's something that crosses across many approaches. But then, of course, there's also the other aspect of holography, which it gets its name from, is dimensional reduction, or if you like, the emergence of space-time of one dimension from a theory which is, you know, of a different dimension, one dimension lower, for example. That's a classic example of ADS, the ADS-CFT correspondence. So I don't know whether that is generic. I mean, other people who work on other approaches can speak to that, perhaps. But it's certain. I mean, the ADS-CFT correspondence is certainly something that has really been taken on board by a lot of people as telling us something deep about quantum gravity. We haven't addressed that. Well, that's not been really included in the program, but maybe people who know about that could just join in the discussion on that. But that certainly, people point to that as a really strong example of space-time emergence. It's kind of slightly strange emergence because it's space-time of one dimension emerging from a theory, a space-time theory in some other dimension. So it's not exactly what many people like Renate and Daniele would say that they think of as emergence of space-time from fundamental building blocks. Non-commutative, well, here I'm going to express the question I just mentioned. The question I always ask when I'm talking to people who work on non-commutative geometry. The question is, can it be made compatible with Lorentz invariance? It always seems to me that it elevates coordinates to a higher status than they really deserve. One of the lessons, to my mind, of general relativity is general coordinate invariance. That coordinates are just coordinates. They have no physical status; they're just coordinates. And so, in non-commutative geometry, it seems to me that they get elevated to a higher status than they really perhaps deserve. Non-locality. I just want to here just not really answer your question, Thomas, but just point out that causal sets are non-local, but they're not acausal. So the non-locality stretches over, in a causal way, stretches over large regions of space-time. So a causal, a space-time atom here can be directly linked to a space-time atom over here, and that link stretches across a large region of space-time, but it's still within the lifetime. So it's not. So just a warning, I suppose, that different people use the word non-local in different ways. Often the same person will use the word non-local in different ways. depending on what time of day it is. So just to be aware that non-locality has different meanings to different people. That's even setting aside the non-locality that people talk about in the context of the Bell theorem. Law correction to the area law, are they discriminating between theories of quantum gravity? To my mind, that depends on whether these corrections are observable or whether they get lost in the approach to the deep quantum regime. So just as perhaps higher derivative corrections to the Einstein-Hilbert term in effective field theory, maybe they are not physically relevant because they, as soon as you are approaching the regimes where those corrections have to be taken into consideration, you're in a regime where the semi-classical approximation is breaking down anyway. So it's possible that that's also the case for these law corrections. I don't know. So that's just something, a question. Yeah, that's it. Thank you.
Thank you. Thanks so much. You know, the honor of being the last one.
My level right, let me get to the bottom. There's a couple of letters.
Couple of letters, okay.
Couple of letters.
A couple of letters maybe. Okay, so yeah, features of quantum gravity. Yes, so I wanted to say something regarding to this more specific questions about non-locality and non-commutativity and degrees of freedom. It's all mixed up, yeah. But what I want to start with, even though I tried to present during my talk how I kind of connect already some of these notions and build non-local theory, which describes a lot of things. Apparently, what is being done, and we understand it, yeah, we have H mu, which is a field, which is spin 2 field, and we are building quantum field theory of spin 2 field on a Minkowski background. Okay, so even this very nice construction, which supposed to, and this already requires non-locality, in my opinion, of higher derivatives. So even this construction is just yet a construction of some theory of spin 2 field, maybe renormalizable and unitary, but it's not yet a quantum gravity in the sense that we are not talking about space and time emergence somehow. We are not talking about quantization of space-time. We are talking about embedding of spin 2 in some way in the spirit of effective field theory, and put it on Minkowski background. And we don't know how to do it properly if background is not Minkowski. Okay? So from this perspective, I should say that I'm going to take some maybe a bit old point of view, maybe not very popular now, but I believe that the best way to elevate our knowledge about space-time would be strings. I don't know, maybe it's not the most popular now, but I like strings. Okay? I think strings will give us a lot of things, and especially I think the string field theory, which is second quantization of strings, will give us a lot of ideas what should be done, because this is at least a solid and unitary and gauge symmetric proposal to address fundamental issues. And strings, they by their nature non-local, so I have no doubt that when we speak about whether at fundamental level we should speak about non-local theory, yes, we should speak about non-local theory. Most people here, they support this view because they, from different perspectives, get non-local theories. And most of you also end up with non-local theories. And effective field theory also has a lot of hints to say that the effective field theory of gravity will end up with some non-local formulation. Okay? But about non-commutativity, it's about different thing. Again, like it was 2 days ago, I was complaining to organizers why they included 3 not connected words in one discussion. I'm not sure non-commutativity is very much related to here, but I have something here in mind. When you say non-commutativity, essentially you mean that operators which correspond to x mu and x nu, their commutator is not zero, which is fine. And apparently, we perfectly know that we already use this for, if I remember correctly, for 70 years, when Landau written that if you try to quantize charged particles, which has some charge in a magnetic field which goes like this, then you must have non-commutativity. Yeah? So there is no issue that we must study non-commutativity, and I think we should study it, but it would be at least strange to me to think that at the fundamental level you have a magnetic field. Yeah, I think at fundamental level, I think it's very good for our understanding how to work with non-commutative series, and we must have them. And particle and magnetic fields already leads to non-commutative quantum mechanics. And the Zyberg-Witten paper is about non-commutative strings in B field. And it was a lot of activity about this. And I know it because I was, when I was a student, forced to compute two-loop diagrams in non-commutative theory. So I know that it is complicated and it is quite fascinating. But from here, actually, there is another observation. Yeah. There is another observation which is coming from here, which we learned studying this series, and which apparently was not very much addressed, at least during this week. But if I know correctly from people, it was a subject here during past week, it is UV-IR mixing. This, I think, is a very nice direction to explore in many regards. This is related to holography, and this is, well, let's say in my study, first it appeared from study of non-commutative field series, but this in general should be a very interesting direction to explore. Actually, would it be, actually I would better speak not about non-commutativity as such today, but rather about UV-IR mixing. UV-IR mixing is a subject which may lead to surprises just because it's an possibility, and also we all know that if we go to strings, we also have kind of UV-IR mixing as long as we speak about C-duality. Yes, as long as we speak about C-duality, which is proven fact for strings, we know that long and short distances, they are connected. So in principle, this would be a very interesting question whether quantum gravity as such somehow incorporates or respects or likes UV-IR mixing to be in any possible construction of quantum gravity which you can imagine. I unfortunately don't imagine any construction of quantum gravity because no one imagines. And as Renate told, that we are waiting for someone maybe to explain us what is quantum gravity. But for the moment, we don't know exactly what is quantum gravity. But this would be my expectation that quantum gravity should somehow be related with UV-IR mixing, which hypothetically may lead to a lot of surprises and a lot of new maybe simplification. Yeah? And another thing which is connected to degrees of freedom, yeah, because it was also degrees of freedom. And this is a complicated question, and here I stay again on a conservative position that degrees of freedom, which we study perturbatively, we all know about them. But when we go non-perturbatively, because we don't know non-perturbative regime, even due to ADS CFT, we still don't know what is non-perturbative. We are completely for example, standard form. Then here the point is that I would say that degrees of freedom, and here I agree completely with Renate, that degrees of freedom require the re-understanding when we go to high energies. Because it's not clear that degrees of freedom in IR and UV may be defined in the same way, unless we will find some nice UV-IR. If we will find one, then I believe that we can keep our IR intuition to say what is happening in UV. So my bet actually for this particular combination of UV-IR as possibility to find something new in, let's say, at least my lifetime perspective.
Thank you. So now it's time for the audience to engage as well. So I'm sure things have been said which you feel strong about, and if so, please speak up as a comment or as a question. Yes.
Well, many of you spoke about the emergence of space-time. I want to hear if you have a precise mathematical definition of what is emergence of space-time.
Yes, but it was told today, yeah?
Yeah, well, is there a let's say universal definition of emergence of space-time? Let's put it this way.
No, the short answer is no.
There are ideas.
There's not even a universal definition of emergence, period.
I want to see. I like the word emergence, and I understand physically what emergence means, but mathematically, then
you want. I mean, you know where you want to get. So, if you want to characterize the notion of emergence in abstract terms, yes, and then you apply it to space-time, as far as I know, you need. It's based on the fact that you have some novelty. So the end point, what emerges, is different in in a number of ways from the starting point, what it emerges from. So this degree of novelty is one ingredient. The other is some form of robustness, because this process of emergence is, in order to be physical, in order to be physically significant, it has to be robust. And normally is the procedure of emergence, or whether it is intertheoretic or it is a physical process, has to do with approximation, limits, and so on. These are the main features. Now, this emergence in general, in the case of space-time, in any formalism in which among the initial ingredients, there's no space-time as defined in your preferred way, for example, in terms of relational observables constructed out of smooth fields. If those are not among the ingredients, and you manage to reconstruct those observables and therefore space-time out of something else, you are going to have a well-defined, conceptually meaningful notion of emergence of space-time. Anything more specific than that, it will depend on the formalism, on your degrees of freedom, what sort of approximation you decide to take. I'm not sure exactly how you can give the definition.
At what scale we can somehow declare the space-time as emergent? Let's say, of course, you're targeting a Planck scale, discretization, but, well, of course, if it is present scales, of course, it is.
There is no space-time, there is no scale. You have to say,
I'm not sure.
Tell us scale in what you want to see.
Compared to Planck scales, is it the Planck scale much greater than the Planck lengths? What kind of length scales you can say? Well, you have the smooth fields, and this concept of space can be.
If I can try to put the question in a much more down-to-earth context, like the emergence of hydrodynamics from molecular dynamics or from atomic physics. But once you have the procedure, so you have a set of partially deductive, partially rigorous, partially heuristic steps to take from atomic description to hydrodynamic description, then you can probably answer your question, because you start noticing that from the effective point of view of hydrodynamics, some features start being pathological and breaking down once you reach certain scales, as defined from the effective field. Vice versa, you can say from the point of view of the atomic physics, if the number of molecules is not at least of a certain order, if a number of other parameters are not of a certain order, I don't expect any hydrodynamic approximation to work. And you can maybe check that in fact it doesn't reproduce the observable quantities. But abstractly, absent a specific procedure that works for reconstructing space-time out of something else, or a space-time emergence, I don't know exactly how to answer the question. What would be the scale, and why should you have that one?
But I just want to comment, there are, as you said, multiple versions of the word emergence. What you just described is emergence that is related to coarse graining, and then the word scale has a meaning. But another example of emergence which was mentioned was, for instance, holography, where the most famous example have a four-dimensional quantum field theory on a non-dynamical space-time. And what emerges, and this is not related to coarse graining, is a 10-dimensional dynamical space-time. So there you have the word emergence, which in my opinion has nothing to do with coarse graining. But
yes, but if I can just add just a very brief comment there. Frankly, I'm not so sure that you would be justified calling it emergence.
Okay.
If it is a duality, I think that it will not qualify as emergence because it's an exact dictionary between one way of writing things and another way. And that's also why, because it's an exact duality, there's no scale. There's no approximation involved. It's just a translation.
Maybe you want to comment on this?
Maybe I think there are different possible notions of emergence, and describing something where you emergence from some, say, microscopic degrees of freedom. But let's take another point of view. So if, as I was advocating, the fundamental thing is not space-time, it's something like the appropriate Hilbert space with an appropriate mathematical structure, well, how does space-time emerge in that context? Well, let's first remind ourselves where space-time is if we're just talking about quantum field theory in the algebraic approach. And where space-time is it's encoded in the net of subalgebras of the algebra of observables. That net has a structure of subalgebras which are roughly in one-to-one correspondence with open sets, with intersection relations, with inclusion relations, just like the open sets of topology. And so it's in the algebra that the space-time is, in the case of quantum field theory, precisely encoded. Okay, but if we have some other mathematical structure on the Hilbert space that only reduces to that net of algebras in some limit, sort of G goes to 0 or something like that, then you wouldn't have necessarily an exact notion of space-time, in that more fundamental mathematical structure. But you would only then recover it in the limit where that mathematical structure went over to this net of subalgebras of sort of in the G goes to 0 limit. That's another completely, I think, orthogonal way, or at least very different way, that you could imagine space-time emerging as a mathematical structure from something else, namely Hilbert space and appropriate mathematical structure.
Can we say differently? Like, suppose when we start to see dynamics of space-time of some scale more profoundly, can we say that as a emergence? So like you have got dynamics in the space-time, like for example, expansion of the universe and black hole formation. Whenever you start dynamics, can we call it an emergent? Someday. Another definition of it. Maybe I understand what you already tried to say, but
yeah, so maybe it goes, a little bit in the direction that wasn't part of your comment, since the concept of the local algebras seems to be sort of orthogonal on the idea of gravity because of the non-locality, I'm not sure that's the best starting point, but it's well worth exploring. I would go to talking about observables, right? So that again is a different notion of emergence. For instance, if I understood correctly, for instance, she's very much and other people after having a G mu emerge in some sense, right? For me, the G mu was in a way part of a classical formalism that of course works extremely well, but one should remember that when we do gravity experiments classically, we don't observe local G mu's, but you look at observables that typically also have just non-local features in them, because that's the nature of gravity, right? And so it's really different from our field theories. So I would say a minimal version of emergence is you identify at least, the more observables you can show have a large scale limit that fits with Einstein's theory, the better. But it will, again, things you mentioned, it will not work for arbitrary observables, because those you're thinking classically, like observables I used to discover cosmology, the whole thing. I think it's asking far, far too much that all of these features should emerge from quantum gravity. I think that's unrealistic expectations to have. So some things you may be able, to show that emerge, and so you will accumulate some evidence, that what you're matching onto is indeed something that is just perfectly describable by Einstein theory, but you will not be able to reproduce every element of even of the classical theory, because I would say most of these are not in the strict sense observable.
But if I can say what you were saying is true, it's just that you have to check that as long as possible list of observables that are different variant and blah blah blah, in some regime behave like they would do in Einstein gravity. So I agree, it's in terms of observables, not the formal structure of Einstein gravity or the Einstein's equations per se, because that may not be directly physical. But indeed, part of showing that space-time as we know it emerges, or the gravitational theory emerges, is showing that the dynamics is reproduced of appropriate observability.
Just to follow up, sorry, please.
Yeah, many people want to comment. So
Well, I wanted to respond to a comment, and so in particular, you made a critical comment about thinking about the algebra. So, we're physicists. We need to explain physical phenomena, not just gravity, but everything else. That's our job. And we have a lot of observational evidence for pretty much all the other things in the world except gravity, right? And those, we're in a regime where gravity is sort of a weak effect in most purposes. And we have an extremely well-developed formalism for describing pretty much everything else except for those gravitational corrections, and that's local quantum field theory. And there, the observables form subalgebras the observables form algebras, and an important structure is the subalgebras of those algebras. So that structure is very well defined and well understood. And so if we're thinking about describing physics in a regime where gravity is for many purposes a weak effect, we should be looking at small corrections to that. And so I think that's a perfectly reasonable structure to start with. And, if you're talking about quantum field theory and you want to discuss observables, that's what you talk about. It's the algebra.
No, I think I started by emphasizing, really what I'm talking about is really the UV regime, and it's unclear, whether thoughts that, as I totally agree, are working and seem to be working just fine in describing low energy other common theories, and hopefully of something like perturbative quantum gravity may be relevant. But these two regimes, what is a very good description in one regime may not mean another. So, I would, to what you presented, coming from also IR considerations, because that's most of your motivation. Well, some of these things you can ask, what survives? Will Hilbert spell survive? I'm not advocating non-locality. I'm just talking about non-local properties of observables. That is already there in the sense I described, but it doesn't mean classical DR is, non-local. I mean, you're still writing down local Lagrangians, right? So in that sense, it's perfectly local.
I've seen many fingers. If Alexey, you want to comment on this?
Let me pass and let other people continue. There are various things I would like to respond to, but I don't want to.
Right. Well, you wanted to say something?
Yes, I just had a simple question. You do quantum gravity, different methods. Do you get the graviton or not? Do you expect to get the graviton or not? And if you compute the theory, do you expect that if you take h bar to 0, you get classical gravity or not?
So Daniele already responded, so it's for the, I guess it's a question for Faye and for
The answer to your question in causal set theory is bound up in this question of whether there's a continuum regime at all, and whether the histories that dominate the sum of the histories are solutions of the Einstein equations. If that's the case, then I think the usual, it's likely the usual effective field theory, derivative expansions, arguments will essentially guarantee that there will be massless propagating degrees of freedom, so you would get the gravity. But it depends crucially on this aspect, this question, which is something Renate has always emphasized, which is, do you get a continuum regime? So how is the entropic weight of all the non-manifold like configurations to be suppressed? Can it be suppressed? Is it so? And that's an open question in our theory. So the answer to your question is we don't know, but it depends on achieving for example, in the first instance, we have to achieve a continuum regime to show that exists in the theory.
Can I just clarify, just to say that one is a kinematic statement, which is like kinematically, it's possible, you can, but dynamically, whether you have emergence of continuum-like spacetimes or not. So kinematically, we know, but dynamically, we'd have to prove it. So I think there's no fundamental contradictions. I don't know if that helps or you're looking suspiciously. Yeah, but I think, yeah, that's sort of.
What do you mean?
Kinematically, in the sense that the structure of the kinematics of the theory allows you to have gravitons and everything, all the lovely stuff. But we don't know from our fundamental thing, putting all these ingredients in, whether space-time will emerge. We know bad causal sets don't, but we don't know space-time like ones really do.
You're saying that spin 2 objects seem to come out, but you don't know whether they obey the Einstein equations. Is that what you're saying?
Yeah, multiple things. We don't know multiple things dynamically, because that would mean solving the problem. I think it would mean solving the problem fully.
So
sorry.
So I was just asked to respond also to Paolo's question. Okay. So Paolo, I would expect that, yes, I can reproduce at least aspects of the classical theory, and some I could already show that emergence. I do not expect to find gravitons necessarily, unless going through the classical theory first and then just doing, perturbative theory. So why am I saying that? I'm at least putting it up as a possibility. Well, number one, why does a viable theory of quantum gravity have to reproduce a perturbation series that we know is ill-defined? Okay, and well, we may never have experiments that probe that regime for a reason that also Faye mentioned in the talk, because they're so tiny, the effects, right? It's just the first quantum correction. So the corrections to Newton's laws, they are well-defined to do in a certain order of perturbation. They're well-defined equations in the order of perturbation theory, but maybe I will never, for most technical and maybe even questions of principle, able to probe that regime. So that raises, of course, the question, how physical are gravitons? There are, of course, elements of a certain calculation framework, and we even can compute at some order. We can compute things like scattering apples but are they really relevant to that theory of quantum gravity? It's not obvious.
I think Steve would like to comment on this.
Yeah, I think I have a comment and question related to all of this. So, there's this claim that one has, at least for certain purposes, a non-perturbative approach that UV complete, et cetera, et cetera. One of the things that is really missing is a connection to some of the questions that we really need to answer. And so that directly, I think, relates to this. So let's take our universe. The curvature radius given by the cosmological constant is something like 10 to the 30 in Planck units or whatever. It's huge. Okay. And so in that context, as we see, there are states that look like propagating matter quanta, which we can collide, and we we spend a lot of time observing collisions and seeing what we get when we collide to one kind of quanta and get out some other quanta. And so that is the kind of question which a complete theory really should be able to address, even if you don't accept that flat space is an exact solution. Okay, well, we find that, something very much like de Sitter space with a radius that's way bigger than the Planck scale is an exact, it is an apparent solution that we have, and, that's what we see. And in that context, we should be able to basically consider states where we have an excitation over here and an excitation over here, and they collide, and we get out some interesting stuff, okay? Included, presumably, in those excitations which we can collide should be a spin-to field, or something that's behaving like a spin-to mass of the field. Certainly we observe propagation of, collective, large numbers of gravitons, basically. That's what LIGO does. And so, presumably we don't know this experimentally yet, but you should be able to consider the limit where you have, say, one quantum, right, propagating. So, but again, all of that is missing in this approach. And I think that's something that really, better contact needs to be made with this question of, how do I get something that at least to a very good approximation looks like Minkowski space? And how do I get something that looks like, say, propagating excitations on top of that? And even, in that context, there are important non-perturbative questions, because if I have propagating degrees of freedom in Minkowski space and I take them to be highly boosted, I can consider collisions at very high center of mass energies. And that definitely gets into the non-perturbative regime where I'm doing something like making a quantum black hole. So all of those are very important questions which should be part of a complete description.
Yeah, but you say, should. So the thing is, I'm just not so sure. I'm not so sure that I will be able to physically even prepare those graviton scattering states ever as a matter of principle. I'm not so sure. So I'm just want to put.
There is also tensor spectrum and inflation.
No. I know. I'm talking about individual preparing, not gravitational waves. No one. We have seen gravitational waves, but it's individual. I just want to put up as a logical and physical possibility that this is all the Dowker experiments which have no physical correlate. And let me finish, and then I just want to put it up as a possibility. So that although it makes sense in analogy with all other quantized, fields we discuss on propagating on a flat space, to write this down, and there's a formula that's well defined, but it may not refer to actual physical experiments ever as a matter of principle will be able to conduct. The experiments I will be able to conduct, let me rephrase it, so might be things that if I rephrase them in a graphiton language, would correspond to extremely composite states, which have a behavior where you really kind of maybe need to sum up the full series, or that exhibit stuff that you simply cannot guess by low order perturbation theory.
Well, so in response to that, what LIGO sees is propagating gravitational degrees of freedom on a very low curvature background. Let's take it to be zero. It's not exactly zero.
Fine.
So a question is, how low can the amplitude of those excitations go? They've got a certain amplitude, but is there could we take it to be smaller? Okay, probably yes, right? You can imagine different black hole or different mergers or other things that produce lower amplitude waves. So what's the limit? And at least in the standard quantum approach, the limit's basically given by the sort of production of a single quantum or something, but maybe there's some different story, but you've got to have some completion of that story looking at low amplitude propagation of gravitational radiation, because it's out there and we've seen it.
Well, but still, yes, people are trying very hard to understand, is there any H bar physics I can find in gravitational wave data that may get us a little closer to where you're saying, no, really, no, look, Renate, here, you have to explain this. but we haven't been able to pinpoint such things in a very convincing manner.
So maybe this is actually an important point to the organizers, right? Sorry that I'm intervening. I'm not the expert. No, so the thing that I find interesting, this is a conference where you gather different disciplines, of at least people working on the same question. And what I find interesting when we were discussing over lunch exactly this, is that we disagree with each other, not even on the theory, but on what kind of questions the theory should answer. So we were discussing that, okay, do we all agree that a quantum gravity theory should allow us to calculate gravity and scattering amplitudes? Now we hear that the specialists are mixed on this, and I think it would be nice. I don't want to give my opinion, but as a goal of like this kind of conferences, that we at least can have a consensus on what do we all agree that we should be able to compute so that we can compare approaches. And so now I don't even know what it is, because we even are saying, some people saying gravitational scattering might not be a well-defined question. And I'm just finding it interesting, and I don't know.
We don't all have to agree, but we have to be aware that, you know, we have different expectations.
But it would be nice if we can at least, so that we can have a discussion and to say how good is one approach versus the other, that we can ask in principle questions. Should your theory be able to do this? Like, should it resolve black hole singularity? Should it calculate gravitational scattering?
Well, again, regarding gravitational scattering, I mean, it's happening. You know, there are gravitational waves they're propagating. We're measuring them. You know,
but look, Renate's question is not about whether you can see a very low energy graviton. It's the question: what is the state behind this? I mean, we know some asymptotic limit where, I mean, it's roughly linear, but we know, I mean, if you have any, I mean, UV completion of gravity, this will not be linear in the graviton. So the question is, what is the state?
Anna has her finger up already for a while. I've been ignoring her. Sorry. Yeah.
Well, I wanted just to express some suggestion what can be, at best, what should be computed. I'm not sure if it's relevant for all proposals, but to me, it's kind of almost obvious that we should have a flat space in which we live, or almost flat space living. And also, we should have some spin-2 gravitons in a very weak field regime, producing Newton's law, and also some observations of black hole collapse and mergers recently detected by LIGO, and many other phenomena. So it's kind of essential part of the theory.
Those primordial gravitational waves.
Gravitational waves are not yet seen. That's fine. Let me come closer to the question. So since we should have some states like gravitons with spin-2, they should somehow scatter. And the question is, what is the limit of this scattering amplitude in a very high energy regime? Because which is beyond the EFT description. Why I'm asking this question is that on how these amplitudes behave at very large energies, you can, in principle, derive many things regarding infrared properties of EFTs. Here, I mean that EFT expansion is not random and arbitrary. You have some constraints following from causality requirements from also locality properties in the UV for the scattering amplitudes on flat space will also give some very meaningful bounds on how structure of EFT Lagrangian is looking like. Not everything is allowed there. And if your amplitudes are looking absolutely differently with some weird non-localities, this would be some prediction also for low energy expansion of gravity Lagrangian or gravity matter Lagrangian. This is still very far from real experiments, but in principle, in the early universe, some effects can become emergent,
right,
which are relevant to additional vertices in EFT Lagrangian. So that's, in my opinion, kind of important problem which probably should be addressed, but of course, I guess some proposals could be very simple.
So there's Daniele, then Claudio, there's a lot of, so the order was, yeah.
So when I first raised the finger, I had the ambition of reconciling. I start feeling that was maybe over-ambitious. So let me just state what I think is what is my view, and then we'll see how much it reconciles with the others. So personally, I think that it should be a goal of any theory of quantum gravity in which spacetime is emergent or not, it doesn't matter, to reproduce perturbative gravitational physics, including gravitational waves, because that's what we observe in all sorts of backgrounds and so on. This is, I think,
Classical gravitation.
gravitational waves. Gravitational waves, I haven't quantized anything yet. Now, in fact, also you mentioned that, and definitely it should also be possible to derive that and then quantize the corresponding perturbation. So at the level of effective theory, effective quantum field theory of a certain subset of degrees of freedom that are first derived classically, I think nobody would disagree that you should be able to reproduce it. In this sense, you have some perturbative gravity theory, which is observationally there. Then you can also apply further quantization procedure like we do with the phonons in a fluid, and you get some quantum theory at this effective field theory level. I was about to say this, I don't think it's controversial, I think everybody agrees, but I will not say that. Now, I think the disagreement starts whether we feel that in a full theory of quantum gravity that does that, the effective quantum theory of gravitational waves or gravitational perturbations should be UV completed in a sense that it can be pushed within the theory to some UV limit without changing degrees of freedom and maintaining this perturbative gravitational degrees of freedom. In this sense, is the question whether the graviton, the quantum of such effective field theory, has somehow a meaning, mathematical or physical, in the full theory. And that's where there may be disagreement. And it translates into the question whether there is a well-defined, in the full theory, single particle state for the quanta obtained from gravitational waves. Now, it may well be that the theory doesn't allow this, and that's the sense in which it's not a requirement in general that the full theory of quantum gravity will complete the perturbative quantization of gravity in this sense. However, I personally believe, and I make no statement again of our share, is the belief that the full theory should have to explain why the perturbative quantization fails and where, in which circumstances, and the physical principle why it cannot be pushed to the UV. So why a graviton doesn't exist as such, but only in some particular regime as an effective degree of freedom.
There were many questions, so I want to know which ones are the urgent ones, given what Mario, you're very
well, I mean, it's directly related to that. So I mean, first, yeah, there's absolutely no need for a graviton to calculate black hole collision. You can calculate that with GR as much as we can calculate water waves. Nobody would have the idea to say there has to be a quantum of water waves. I mean, it's just not. It's at this level, it works. The theory works. We can do everything. And the second thing is regarding the comment. We're in an almost flat space. This is a very dangerous statement geometrically. As soon as you have the slightest curvature, a lot of properties of flat space that we know and love go straight out the window. You lose, for example, Huygens principle. There are other things, like if you're in a de Sitter space, you have way different decay behaviors of certain perturbations.
But not small scale. But that's what Vasilia was saying.
But if it is slightly curved, then it is slightly curved.
At the end, we want to describe the universe, right? We want to have a theory that describes everything, and their asymptotic behavior can be very relevant.
Yeah.
So if I can just interject here with my little statement, which is to do with the S matrix, right? I mean, there's been recent work, I think, of Prabhu and Satish Chandra, where they talked about the infrared issue of quantum field theories and also gravitational theories. And the fact that the S matrix isn't well defined, and that it isn't doing what you think it's doing, which is to take you from one Hilbert space back to itself. And the fact that those Hilbert spaces are distinct and different. So the idea that somehow the S matrix and all of these things are really well defined, even in the infrared. I mean, if we're putting in a lot of, if we believe that the S matrix is the right sort of fundamental principle, I think we already have issues with it in field theories when you take the full, when you really look at asymptotic. So it's not entirely clear to me why you would choose that as a fundamental principle to define your theory. So just so
So that's a different set of issues, I think, and I touched on it in the discussion a couple of days ago. You sort of, the question of being careful about defining the S matrix. Certainly, if you think about higher dimensional generalizations of gravity, you can fix that, but there are other approaches as well. But anyway, I want to come back to this question of, should we have things like gravitons? And let's try to be a little more sharp about that. So first of all, we live in a quantum universe, we think. And if there's a quantum theory of it, then that quantum theory should have things that are quantum descriptions at the fundamental level of propagating gravitational waves like we see at LIGO, Virgo, Cagra. I hope everyone agrees with that, right? Because we've observed them and we're in a quantum universe. Okay, so then the question is there a limit of those things that looks like single gravitons? And also, is there a limit of those things that looks like, say, single gravitons with very high energies? So let's address those in turn. Well, again, you can imagine just lowering the amplitude, basically. And then the question is, how low does the amplitude, or can the amplitude go? In a description in which quantum field theory is a good approximation, then you expect that there's an answer that, basically the amplitude goes down to something determined by h bar, and then, that's the limit, and then you have a quantum that corresponds to a single graviton. If there's some modification to that story that comes from, say, dynamical triangulations or something, it'd be interesting to know what that is, first of all. And maybe there is, it's not even clear how to get approximately flat space and whatever the propagating degree of freedom was. The second question is, can we think about high energy versions, high frequency, high boost? Well, if we have an good approximate notion of Lorentz invariance, then the answer should be yes there, because if we have a theory that has at least a very good approximation of Lorentz invariance, we just look at our originally low energy graviton in a highly boosted frame, and then it's a high energy graviton. So if there's something forbidding us to consider the high energy things, then that should be some modification of Lorentz invariance. And of course, there are very tight constraints on it. So that's another comment. Finally, one comment related to the question of how flat the universe is or isn't, and whether that's relevant. Well, again, the sort of a figure of merit is 10 to the minus 30. Okay, so if I'm going to calculate some amplitudes or something, and I have some corrections to those, which are some power of 10 to the minus 30, I may not worry about that too much. It depends on which amplitudes I'm computing, but I think that there are amplitudes I can compute for which the corrections are something like that. Powers in 10 to the minus 30. Right.
Yeah, I have a very short comment about the scattering of states with high energies. The analogy with QCD is like imagine this QR scattering pions, which are described by EFT Lagrangian, but you still can define very well what is high energy scattering of these pions. It's just the amplitude is something which you have to compute in a full theory, but not in a short field theory.
I think the analogy is more the gluon, and you can't define the infrared scattering of gluons. I wish you find. I think this is also, the gluon, so the graviton and the gluon are gauge particles, and they are both, the underlying symmetry is a nonlinear one, and that screws up with the interpretation of a gluon as a particle in the infrared, and you can boost around as a bit, it's not getting as physical. And now, what is the infrared in QCD is the ultraviolet in gravity. So the much I like the picture, so we have nice gluon jets in the ultraviolet, we can measure them at the experiment. We can't measure anything in the infrared. And that's what I expect in gravity, the other way around. We have a nice interpretation of gravitons in terms of gravitational waves and so on in the infrared, but we have a very complicated picture in the ultraviolet. Right? We see gluons, in terms of partons or whatever in hadrons, but we can't define them.
What supports that picture that if you try to, say, scatter gravitons at higher and higher energies, you have, you know, I know if you go ultraplankton, for example, there are interesting modifications, which we could all discuss, but, you know, if you're suggesting there's some limit to scattering gravitons, you know, maybe some fraction of the Planck scale, what is the important modification there? If you go to higher energy.
That the nonlinearity of the theory hits you hard at the Planck scale. It's evident.
Okay. Yeah.
And then the state is not just one graviton. It's the same like the gluon in the infrared. I mean, the gluonic state is not one gluon.
Well, again,
the best you have is a glue ball.
Well, it's Planck scale. You know, say if you're doing Planck scale center of mass energies, if you're scattering, then you have new effects, which do become highly nonlinear. And, you know, something like formation of quantum black holes is probably a beginning description. But, you know, if you're just thinking about, say, one graviton state, you can get a high energy one graviton state by boosting a low energy one graviton.
You can get a low gluon by boosting a high energy gluon. And now it's not really giving me an infrared state. I mean,
we didn't have the low energy gluon state to begin with either. So we didn't have the low energy gluon state to begin with.
We didn't have the high energy graviton state to begin with.
No, but we have the low energy graviton state.
And we have the high energy gluon. I'm sorry. I mean, if you just make boosts, I can boost from the infrared to the ultraviolet and the other way around. So what is different now? I mean, we are more used to the fact that we have something which is perturbative in the ultraviolet and becomes complicated in the infrared. So we are all happy with the picture that we have perturbative gluons, but we can't describe them in the infrared. But I mean, for us in gravity, it's the same. I mean, our call it infrared gluon is the ultraviolet graviton. So I can't see a difference there.
Well, I think the physics is different between the two, but it would be a more detailed discussion.
I agree, but I mean, in the construction of the states, there's no difference.
I mean, you have a color confinement in QCD, but there is no evidence that you have the confinement of gravity.
We had the color confinement is always a red herring, even without it.
You don't see gluon as a party.
Understand this, but it will not be.
But what is the evidence you don't see graviton as a party?
Well, we have a nonlinear state, and the nonlinearity, I mean, in the infrared is not really, you can make an expansion. We know that, right? Okay, you can make a linear expansion, and we can identify gravitons as we can identify perturbative gluons in the ultraviolet. Right? But now we go to the, if we call it take for just for the time being quantum field theory UV completion, then this will be a strongly correlated theory.
So what's the upshot of this? You don't disagree with the aim of calculating the S matrix, which is only about
No, but I mean it's not. I mean, I think looking at something like graviton scattering is a red herring. It's not leading us in.
Okay, can I rephrase? Because you know, it's completely correct what you stated. So, well, let me say, I won't be able to meaningful study gravitons or graviton scattering in my framework. But that's part, well, a matter of principle, because I am on very short scales, and there is no way to scale my lattice parameters to bring it to an IR scale. That's something that doesn't happen, but that turns out to be the case. So I'm confined to, you know, a universe of 20 Planck lengths or something. So, however, if I'm lucky, right, I'll be able to understand some features in this UV regime that doesn't approximate Minkowski space, you know, by any imagination, let alone gravitons. So these as concepts, gravitons as concepts, simply don't exist at that scale. And I would claim that's not an issue with my formalism, but I happen to have it, you know, sitting there computationally. So I cannot prepare single graviton states. I don't even know what that means. So the logic here is then more saying, okay, by looking at other observables that I can meaningfully construct in that regime, understand something about the theory that's an insight about, what quantum gravity is, and I can compute that may, in an indirect way, down the line, maybe address some of the questions you're asking, and you say that's something that quantum gravity should be able to address, but not in a direct way. So, and so also I'm wondering, you must be also thinking of some, what is the substrate, the substructure of, that, there must be that approximately flat space. So what is that substructure? How is it legitimate to ask where does it emerge from? Or how are you thinking about, the genuinely non-flat stuff? So what is that in your case?
Well, I think if you take starting with quantum mechanics seriously, then space-time is quite possibly not a fundamental structure, or perhaps even some discretized version of that is not a fundamental structure. And maybe the basic thing is Hilbert space or some version of that with some mathematical structure on that gives you something like a quantum space-time.
But Hilbert space of what? All Hilbert spaces are the same.
No. Well, though there are a lot of different things that can live on Hilbert space.
Yeah, sure.
So
I'm asking about
there's some additional mathematical structure, and again, I think a paradigm for this, how this kind of thing can work is in the algebraic approach to quantum field theory, where you have Hilbert spaces that then are endowed with this net of subalgebras of the algebra of observables, and again, that net literally encodes the manifold structure of whatever space-time you're talking about the field theory on. So that's an example of how you can have something that, in that case, exactly corresponds to a space-time as a mathematical structure on Hilbert space.
But as you pointed out yourself, you pointed out that's a non-locality.
Well, there are corrections to that in gravity, right? That structure is not the correct exact structure when you include gravitational effects. So there's some other structure, and I think
I'm curious. Question. Yeah, I'm curious whether you have a specific vision of what that might be, because this is kind of the type of question I keep, is central to what I'm doing.
Well, there are some sort of initial ideas about what that structure might be, but no, I think that was one of the questions that I kind of put up is, understanding how we think about subsystems. Somehow it's the structure that gives us, what space-time would give us if we were talking about field theory, which is, a notion of localization, neighborhoods, distances, and so on, and understanding, what sort of replaces that in the quantum theory of gravity, I think, is part of the central question.
That's very interesting.
But the reason I refer to algebraic quantum field theory is because I think that gives us an example of how what we ordinarily call space-time can be encoded in a completely different looking mathematical structure, and then the idea would be that in gravity, you have perhaps, a mathematical structure with some, at least, analogous features. I'm not sure if it really is the algebra of observables as opposed to another structure in the Hilbert space. That's a longer discussion. But then, space-time itself would only be an approximation to that in the sense that in this sort of limit where G goes to zero, G Newton goes to zero, you would perhaps get out, for example, the algebras, the net about subalgebras of the algebra of observable.
Yeah. So I mean, I was really putting, what you think this is, because even if you're starting talking about, subsystems or regions and work as with those, Of course, it's fine to do that in standard QFT because we know what a region is. I'm drawing a surface, bloop, here's my region. But in the setting of dynamical geometry, it's much less obvious that that's the thing to do.
No, yeah,
Yeah.
so bottom line is, an alternative is, Hilbert space plus some additional mathematical structure, which is something like this net that we talk about in algebraic quantum field theory. But, the problem is to figure out what that algebraic or what that mathematical structure is. And I think we have important clues, but we don't know what it is yet.
Hey, did you want to comment on this at some point?
Oh, it's going backwards. So
It's going backwards.
the discussion has moved on.
Yeah, then, Robert, you had a question.
Yeah, so this is of course a very interesting kind of approach, it's Hilbert space kind of approach. So what I am wondering is that, so in practice, of course, all states in the Hilbert space are just representations of physical systems. We don't know of any Hilbert space and states in Hilbert space that live in abstraction in reality. So now, if one expects this kind of Hilbert space structure underlying gravity, so normally as a naive person, I would expect that, okay, this Hilbert space actually corresponds to some quantum system. There are some degrees of freedom. And then the question is, would it make sense to be able to use this structure and compute the properties of that microscopic quantum system?
Well, I think you're putting in some various sort of additional philosophical ingredients in that set of statements.
I think it's not philosophical, it's reality. I mean,
well, that's some version of what quantum mechanics means that you're stating, and I think it doesn't necessarily mean that. I think we need to
only quantize physical systems. I mean,
well, that's one point of view.
Okay.
But I think, well, again, an example is field theory. If you think about it algebraically, one way of thinking about what it is sort of the Hilbert space is basic. That's the basic thing, and with some additional structure. And in fact, there's an approach to sort of deriving quantum field theory that's very much in that spirit, where you start out with, what is quantum field theory? Quantum field theory, of course, describes everything we know except gravity. So it's a pretty good thing to think about. What is quantum field theory? Well, quantum field theory is something that you get when you try to reconcile the principles of quantum mechanics, of Hilbert space, etc., with the principle of locality and with the principles of Poincare invariance. If you try to put those three things together, there's a folk theorem that you get out, quantum field theory, and that describes everything. All you need to do to get, what we actually see, the standard model, is just state what some of the representations are in the matter constant, etc. So you can sort of derive quantum field theory as an answer to a question. What comes first? I don't know. But a plausible, well, at least you can't convince, or it's hard to convince me, maybe you could, that you shouldn't say the Hilbert space comes first. Okay, what is the most basic thing? I don't know, but a plausible answer is the Hilbert space with some additional structure.
Comments on this?
No, it's a different question.
I say, are there still comments on this particular issue?
I mean, I have a comment. I mean, I understand that is a valid point of view, exactly. But that's not something that we have ever seen. And even in the context of quantum fields, you can always build quantum fields just by starting from the fact that you have particles interacting, you represent them by abstract states, you sum up you encode the effect of particle interactions into an object that you Fourier transform, it becomes a quantum. And then you say, okay, it has mathematical properties, you put in symmetry, you get a Lagrangian, but you can construct quantum field without knowing anything about quantum field. Just assuming from the basic principle that states, every particle is represented by a quantum state, it has a momentum, it can have interactions. You say, okay, let me use creation and annihilation operator to describe interactions. You package them together into a quantum field.
Yeah, I agree that is one way to get to quantum field theory, but I'm just pointing out it's not obviously the only way. And maybe we should be thinking about the other ways, because we have tried to apply that paradigm, in fact, to quantum gravity in many ways, and we've gotten into a lot of trouble. So,
Paolo has a comment on this.
I think the question is, you quantize a theory. What is the spectrum that you find? I would say that this is an important question.
Yeah, but you need a.
What is the
you
spectrum
have
of
Hilbert
particles
space
that you
first,
find?
and then you have observables, and then you have a spectrum.
Yeah, but how you correctly mentioned is all Hilbert spaces are the same, and spectral theorem applicable to anyone.
No. Of course, the dynamics is different, and
Yeah,
the Hamiltonian is different. And the observables are different.
say a privileged class of observables or possibly other stuff.
We're getting close to the end, so I think you want to switch topic.
Well, it's a question still related to the same discussion, but still a very grand question applicable to many of us, especially to the panelists. Basically, I mean, well, we have different theories of quantum gravity, and as Thomas mentioned in your introduction, that degrees of freedom, finite or infinite. Maybe everyone agrees that we must have only finite degrees of freedom. Maybe
no.
I don't know. I mean,
not everyone agrees, but
okay. Anyway, at least for me, it makes sense to have a quantum gravity theory with finite degrees of freedom. Infinite is too much. But anyway, do we have common grounds on observables? Do we have a universal way of defining observables? Okay, whatever the approach of quantum gravity which we like, we calculate the same observables or not. If not, then we are in the serious trouble. We are not in the common grounds. So
do we have them in the classical case?
Right.
What are all
observables? You have been talking about all the observables all this time.
But I don't want to
gloss over. I have observables, but they're not so easy
to
do.
Not everybody
no,
observables. Let's say correlation functions, what you want.
No, that is one of the challenges of quantum gravity is to define the sort of nice sets of, or the nice kinds of observables and connect those observables, with, say, a theory of observation or measurement.
Yeah, I just wanted to stress that that's already a challenge in the classical theory. Of course, everything is simpler than in the quantum theory, but to construct the diffeomorphic invariant observables, including the dynamic of gravitational field, is not a trivial task.
It takes some work, but for example, the people who studied, say, gravitational wave observations have sorted this out. How to make predictions.
We have a lot of answers, especially in various cases. We do gravitational physics. So of course, the answer is known, but I just want to specify that you're pointing to an issue which is already a challenge to do it properly in the classical case. In the quantum case, we lack a lot of structures that allow to solve the issue in the classical one, and so it's even more challenging.
Well, I'm asking if the understanding of the issue of observables is the same for all quantum gravity explorers.
So I have to you a very simple comment from pure mathematical point of view. If, especially in the context that space-time can be emergent, dimensionality is the most trivial observable which you can try to challenge, because you have to somehow emerge 4 dimensions. First of all, in which we live. Okay, maybe it should be embedded in 10, but with this you can start. Yeah, it's a challenging question.
Alexey has a comment on this.
I have a comment on Javan's question. So I believe that, okay, it is true that like in the ultraviolet we speak clearly very different languages. It can be because of such, can be because of dynamical triangulation, synthetic string theory, whatever. But at the low energies, we do have a common ground, I believe. That is effective field theory. Effective field theory is nothing but a way to parameterize ultraviolet corrections. So, and of course, like in effective actions, individual Wilson coefficients will depend perhaps on gauge and stuff, but there are certain combinations of Wilson coefficients which enter amplitudes, which should be independent of any scheme, and those, in my opinion, are not the only one, but the one possible way to compare the predictions of different approaches. And I think you don't really need to perform the experiment with a single graviton, to write down these combinations. They are just, if you want, mathematical ways to parameterize the features of your theory.
So we go back to the beginning, right? This is back to the question of the graviton scattering, and I think it's a good point that we could say, let's not use the word graviton scattering, but is it okay to say all of us with different approaches, can we at least go to each other with a piece of paper, say, I calculated this Wilson coefficient, which for us would appear in graviton scattering, but okay. And then we can at least compare approaches or not.
No, I cannot. As I say, I cannot even, I'm not in a regime where, space-time is approximately flat. So it's not operationally well defined. But I would put out as a candidate, so I think we are far from saying, so what is that would kind of be the maximal thing, what's a complete set of observables, right? That describes quantum gravity in all scales, including UV.
That's my question.
Yeah, so I would say, okay, that's, well, do we have a good answer in other quantum field theories? And to some extent, it's endpoint functions, I would say. So I would say the hottest candidate are maybe diffeomorphism invariant endpoint functions. So, and I showed you a toy example where I computed in my framework a 2-point function. Of course, in a regime that is not at all perturbative. Anyway, it was a term,
They must be related, so maybe in some way, like the amplitudes with the correlators.
Well,
I mean, there is
maybe in some in some limits, but well, that's more speaking, but who can compute these beyond low order perturbation theory in any perturbative approach?
No, but that's already a good starting point.
Well, it's a good starting point, but unfortunately, even if you do like PFT and stuff, well, you get stuck very, very fast because you cannot do the computation. But
that is a computational issue that requires.
It's not it's a computation issue, but if you with all the available, maybe artificial intelligence will help us a little bit. But if you just cannot do the computation, then I have nothing really to compare to in my UV.
Yeah, that's the problem that comes on top of that. I mean, it's you have an observable, but it is practically uncomputable. What do you do with that?
Well,
We are going a bit over time, so maybe Daniele, you had an urgent comment on this particular.
Maybe it should give priority to the others that spoken enough. Otherwise, you have to have a comment.
Yeah, I mean, I kind of had a related one and a slightly unrelated one, but very quickly.
Yeah.
Like, so I think to the extent that these observables can be defined, and in some respects, it would be a bit wary because of like, the issues that if you perform local measurements sharply enough, you make black holes and so on. But even that aside, these things should be, at least in some low energy regime, they should be encoded by these combinations of Wilson coefficients that Alexey pointed out. And so to the extent that going to that regime is a purely technical issue, in principle, the question should be well posed to like, how does what kind of predictions relative to these EFT quantities you get. And the second thing I wanted to say, which is unrelated, is that still within this framework of purely EFT in the perturbative regime, which is not the same thing, but doing both things. And I'm mentioning this because no one has on the topic of non-commutative geometry. There are some recent papers by I think Marcus Frob and collaborators, where using just purely perturbative and effective quantum gravity, the relational coordinates that can be defined in a diff invariant way in this regime actually exhibit this non-commutative behavior very generally. So it's not like doesn't seem to be an exotic thing that appears sometimes, like if you turn on B fields in string theory, for example, or other things. It seems to be a fairly general feature that could also be some sort of common ground.
That's just the modification to the algebra when you include gravitational dressing that I mentioned earlier.
Yeah.
It's the same, basically
yes,
the same story.
My point is that in this particular regime, it seems to be very concretely computable, at least the very lowest non-trivial order. Because the leading order is 0. Yeah.
Maybe on this note, we...
You wrap it up.
Yeah.
Is you sure? Yeah?
Yeah.
Okay, so I would say let's thank the panel members here for doing it.